Okay, here we are. Ladies and gentlemen, thank you very, very, very much for being here with me tonight. This is uh, this is this is you we have screen. Can you hear me? Please tell me if you can see and if you can hear me correctly, because this seems I seem to be streaming well. Please give me a confirmation in the chat if you can hear me and if you can see me. Hi Carl, we hear you and see you. Hi Otosi, another B2A. Carl 5x5, Canon Fodder, oh, nice to see you, all is good. Michael A. Mayo, Pascual Fernandez, Jost, loading, please wait. Uncle Heavy, Jacob Rudder, Abraham Dozer, Blue Internet, Dennis Azurbiaga, Fast Mover, A+, okay, oh, good. So we are. So, welcome everyone to the live stream tonight. While we are here to so first an explanation why we are here discussing live rather than together live, rather let's start the party. Okay. Why we're here with a live rather than having the usual video on the weekend. The reason was that what I was planning to do is to make a video based on stealth on the lesson, wanted to make one in depth. And when I actually wrote the script, prepared the presentation, because what I was going to do is to do something in the format of a lesson, less than the usual documentary, so a little less b-roll, a little less elaboration, more of a lesson, obviously using PowerPoint. But pretty much yesterday night I realized that I had no hope of making a video in time for this weekend. So I thought, yeah, let's do it this live because it's going to get better. I mean, this is going to be probably long. We have quite a long presentation to go through. We are going to cover stealth from a very conceptual point of view in a way that could be used in, say, an educational setting. But obviously the purpose is always to have fun and to try understanding something better. I will try to keep an eye on the chat. So if there is any, I will probably won't be able to answer all the questions all the times, but I will try to keep an eye so to see if something is clear or is not clear. If something is not clear or you don't understand, don't hesitate. Just drop a line in the chat. I'm happy to stop and coming back. We are here because for this thing, probably this kind of format is even better than what I had in mind. Is probably better because because there's some interactivity. We are here. We are here to have a chat. We are here to talk together. And well, 64 viewers, 65, still growing. That is great. I mean, I'm really humbled when these kind of things actually happen. And so this is basically the reason why we are here and why I am doing this. I had the opportunity to chat with some of you before the stream, which was great. So let's see who we have. Fast Mover 45, great. Mystica, hello. Pascal Fernandez, hello. Andrew Moore, FL 300, Christian M, Edu Grand Phone, Blue Internet, Go/27, Joost van Week. I hope so. That's the pronunciation. Apologies if it's not correct. I don't mean any offense. Shroom Shed, from the Discord. Shroom's Need, from the Discord server. Yes, this is the MacBook webcam. I was incapable of making the Canon M50 working on the Mac with Stream Deck or OBS. And that was the reason why I was pretty much swearing this afternoon, because there was no way of having something relatively simple like the drivers for a mirrorless camera working on the Mac. Hugo Misig, formato Ramzal. I'm giving the time to the people to connect. Tino Tenda Nanjari, Tuai, Hal 9000, Zigzag, Grand Zero. That's a very strange name. My friend, Enrico Negros, Sir Gods. Okay, so a lot of nice people in the room tonight. So I suppose we can have a start at this point. Okay, let me change. Good. So, low observability in aircraft design. What we are trying to cover tonight are the foundations of low observability, which is commonly named stealth, and we are trying to cover them in a roughly rigorous way. As usual, few formulas and a lot of concepts. Every time it is great job on the X29. Thank you. Okay, thank you. Thank you to you, actually. This is, I mean, we are trying to go through, we are trying to go through through the details of this of this discipline, and we're in a way that pretty much should give us the basis to understand what's going on. What's important, I suppose, to us as people who are passionate, as enthusiasts, aviation enthusiasts, is understanding which are the problems, understanding why things are done in a certain way. Obviously, the details are very complicated, and you need to have solid engineering background, which I may or may not have. I'm not omniscient. I don't know everything. I'm not capable of everything. You need to have very solid engineering background, and a lot of the cool stuff and the key stuff is actually secret. So we have pretty much no way of getting into some details. But there is quite a level of depth that we can get into, and that's what we are trying to do today. Now, I actually spoke probably too much, but I gave time to the people to try to join the live stream. We are at around 80 people, and this is absolutely great. Oh, thank you, Mr. Ban. It's really appreciated. Sure, the live stream will be available. I will probably use segments of the live stream to make some short videos or anything like that. So without further ado, let's start. Okay. Since people always wanted to know something about me, okay, my actual name is Gas. Actually, I am 53, almost 54. I have a master's degree in aeronautical engineering at the Polytechnic Institute of Milan. I'm a veteran of the Italian Force, but I'm not a pilot. I was a technician, working on electronics and telecommunication. I'm obviously the founder of the channel, and I am a lifelong aviation enthusiast. Is this giving me any qualification to speak about aircraft, to speak about all these things? I don't know, probably, but yeah, let's go, okay? I don't pretend to be anything that I'm not. Okay, according to Wikipedia, and if it is on Wikipedia, is certainly true, stealth is a subdiscipline of military tactics and passive and active electronic countermeasures, which covers a range of methodologies used to make personnel aircraft, yada 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 yada, less visible and ideally invisible to radar, infrared, sonar, and other detection methodologies. Corresponds to military camouflage for some parts of the electromagnetic spectrum. And yes, that's stealth as a concept is probably as old as warfare. And so it's probably not, it's used, obviously, is obviously used largely, but it's probably not the best way of defining things. It's probably not the best word to define this group of technologies and this concept of these thing, this concept relative around stealth, this operational concept and so on. So what I actually prefer is the term low observable technology. And yeah, that is a technology to reduce the possibility of being detected. So we can split the design in three about this. Non-low observable designs, where no consideration has been given to low observability during design, which has been the case for the aircraft till 2 or 3 decades ago. A low observable design, a low observable aircraft is basically an aircraft that is being designed without really considering low observable technology, but it has then been modified and thought again, thought again to add some low observable elements. One case that we all know is the F-18 Super Hornet that had some radar absorbing material added, some blockers for the engine added. Or another element which is quite interesting is the Rafale. The French actually call it a semi-furtif aircraft. And if you look close on the Rafale, you notice that there are some serrated panels, and there are a number of elements that are they are aimed probably to reduce the observability. The VLO, very low observability projects, are those where the key requirement was stealth, or at least one of the key requirements was stealth. And these are the aircraft that we call stealth, we properly call stealth, the F-22, the F-35, the Su-57, the J-20, and so on. So low observable is probably better naming, better nomenclature than stealth, just to be precise, okay? And there is just one rule to be low observable: do not emit energy, do not reflect energy. So there is no communication between 2 points if there is no exchange of energy, if there's no energy traveling between these 2 points. If there is no energy traveling between the target and the sensor and the observer won't be capable of seeing the target. And the rule is that the energy can either be emitted by the target and can reach the observer, or can be emitted by something else being reflected by the target and then reach the observer. You have to minimize both. And since many of you will know that pretty much no object, every kind of object emits electromagnetic radiation, always, save but one condition, which is 0 Kelvin, the absolute zero temperature. So pretty much there is no way of there is always energy in the game, no? And we are talking here any kind of energy, in the sense that these technology, observable technologies, stealth technologies, are concerned about different areas of the electromagnetic spectrum mostly, but for example, sound, even if it's not particularly used to identify aircraft, to detect aircraft, or is a phenomenon built with waves, with energy associated with it, and yeah, that could be an element that could be used. That given that sound is not very relevant in the aircraft. Does data link and radio count as emission? You bet they do. Okay. So in practice, to detect an aircraft, humans and the technology that humans create use three bands of the electromagnetic spectrum: the visible light, the infrared, and the radio waves. You could argue that ultraviolet now has some applications, but yeah, it is definitely a marginal technology. Very quickly, because this is sort of self-explanatory. If you are here, you probably already know what we're talking about. Visible light is just the light that we see, that is emitted by the lights that I have around me that actually hit me and then are reflected by me, get into the camera. They're turned into bit, and they go back to your screen until there is a computer on your side that will rebuild everything. We rebuild the bits into light patterns, and they will show them to you. Sir Gods, how come no stealth-shaped fuel pods and missiles? Not true. Not true. They do exist. We'll speak later. So visible light is clear what it is. The infrared is normally associated with heat and is normally associated, consider the thermal radiation, but in technically speaking is an electromagnetic radiation which has a wavelength which is slightly higher, slightly longer than the visible light, and it is the kind of energy that is always emitted by anybody that has a temperature above 0 Kelvin. Radio waves are the kind of electromagnetic waves emitted by radars, emitted by radio, emitted by any kind of electromagnetic technology, or in pretty much any electronic device, is often under the form of electromagnetic interference. So, about stealth, lower observability, invisible light. Well, it's called camouflage. It's been around since the beginning of aviation. We are not covering it here because it's an interesting thing in itself, but it's not the kind of stuff we are going to cover. But I took the opportunity to plug shamelessly a picture of the Air Macchi MB339K, which was the light attack version of the Air Macchi 339, which it was a very unlucky design, but in my opinion was quite an interesting proposition. But anyway, so we are not talking about camouflage. Those of you actually passionate about those incredibly cool Russian camouflages, apologies, we are not talking about those. Infrared is infrared, as we said, is a frequency that is actually nearby the visible light. It is the radiation that any warm body actually emits and can be actually emitted by the body itself, as we see in the picture, or could be on this planet, can be of solar origin, or even for ground from ground origin. Electromagnetic radiation is the emitted electromagnetic radiation by radio, data link, radar, navigation aids. Actually, an aircraft that has no concern about low observability, no concern about stealth, is actually emitting a lot of electromagnetic radiation that could, in principle, be used for detection. And obviously, an aircraft also reflects, normally reflects the radiation from radars and other sources of electromagnetic radiation. Recently, there have been systems that actually use, for example, the reflection from cellular mobile telephone towers or radio stations to do the detection. We don't know much about those, but anyway, in general, any kind of radiation could be used. So, which are the technologies to improve the infrared low observability? Well, the thermal management of the airframe, basically cooling the airframe, because an aircraft gets hot for several reasons, because there are internal parts that are hot and generate heat, or because can get heated by the friction with the atmosphere, and both are in both situations are generators of infrared radiation that could be used to spot it. Obviously, the jet plume and the hot parts of the engine are a powerful infrared emitter, so cooling the plume or doing some occultation of the plume is important, and finally tactics, which is something you can always do. Someone before the stream was starting actually asked me, what if is actually flying up to the ground be considered a form of stealth? Yeah, potentially, yes. It's a way of actually concealing yourself and making sure that the energy you're emitting doesn't go very far. So in this sense, it's a tactic, and in this sense is a part of stealth. Technologies in the electromagnetic domain that that include that can be used to improve the low observability are obviously stealth data links and radio, which are either directional or emitting in bursts, or using several different frequencies. They're changing frequencies continually. Low probability of intercept technology actually normally applied to radars, which means the same thing, which means normally irregular emissions in various directions at various frequencies with different waveform. There's the shape of the airframe, which is one of the main subjects we're going to cover now. The construction of the airframe, how it is built, the radar absorbing materials, eventual active technologies that someone in the chat has just mentioned about the Rafale, saying I don't believe it has it. Sort of me too, but you never know. And obviously, again, tactics from this point of view. So let's start with stealth in the electromagnetic domain. By the way, I forgot to say something. If you are really interested to these things, please go to a website that is called Aircraft 101. Those who are already familiar with the website will recognize that I used a lot of material that was on the website, because they have a fantastic collection of pictures, images, tables, charts that can be useful to explain this. So kudos to them, absolutely 100% recommended website to visit. I will add the link in the videos or in a pinned comment when the stream will be over. It's something that I suggest you to go and watch. So, electromagnetic stealth, electromagnetic low observability. So, which way the electromagnetic radiation can interact with the body? Well, it can be reflected. You're familiar. It is exactly what it says on the tin. When you see a reflection on the screen, you see a reflection on a window or on a mirror, is electromagnetic radiation being reflected. It refracts, which is moving through two different materials, maybe from the air, then moving into the glass, or to the air, moving into water, for example, are the classical example. The direction of propagation of the electromagnetic radiation changes, and this is another type of interaction. It may be scattered. So when electromagnetic radiation interacts with particles whose size is pretty similar, same order of magnitude of the wavelength, tend to be scattered around. It arrives from one direction and is scattered in other direction. There is diffraction, which is the form of interaction that scatters around the radiation as well, but occurs around the edges or sharp elements. There's interference that occurs when two electromagnetic waves actually occupy the same space, and that's the basis of the active technologies. Can be absorbed, so electromagnetic radiation can arrive on some material and then be absorbed by the material. That's what radar absorbing materials actually do. Obviously, the radiation to arrive onto something, onto the target, and needs to have been emitted before by something, and so it can be emitted. Then it can propagate. Can obviously propagate. It just travel through anything, through air, through the vacuum, to other materials. And finally, it can be polarized, which is something more complicated to explain, which is not 100% relevant for what we are discussing now, so I will sort of skip it. Please consider I'm not your physics professor, so I'm probably not the best physics professor if I wanted to explain these things. So, but this is just an idea of the kind of interactions we will have to deal with to make an aircraft low observable to the radar. Questions? Don't go. Please stay, don't go. Please stay, don't go. It's way better than you think. Please don't go. Please don't go. Okay. So, and the picture on the left is a drawing of what an electromagnetic wave is, which is basically an electric field and a magnetic field that propagate in space through a medium. Well, it can also propagate into the empty space, the void, and so on. But that's the way. It's a wave. So so basically is electromagnetic energy is also is actually a wave. It behaves like a wave. It interacts with things like a wave would do, and it has and obviously at this point the characteristic element is the wavelength, which is, as you can see in the drawing, it is distance between two homologous points, so to maximums of the value of the, in this case, of the magnetic field. If we calculate one above the wavelength, we get the frequency, which means, and this is something that can be a bit complicated. If you sometimes you also have to stop and think about that. High frequencies means short wavelength. So high frequency, low wavelength. Low frequency means long wavelength. So low frequencies means high wavelength. They are inversely proportional, okay? Keep in mind, because normally in normal parlance who is used to these kind of things alternates low wavelength and frequency, giving for granted that someone actually understands that if you're talking long wavelengths, you're also talking low frequency and vice versa, which may not, if you're not familiar, may not be true. Keep considering that. Then, on the top right, there is a small equation you don't have to care about. That's the equation of the equation in itself. You don't have to understand it. It's the equation that expresses the density of energy, and we said we need to have energy traveling for the detection, expresses the density of energy of an electromagnetic wave. What's important to understand here, that there are two constants, epsilon and mu, which are permeability and permittivity, which are related to the electrical and magnetic field. And these properties, these constants, these coefficients, are actually coefficients that are characteristics of a piece of material. You have a permeability, a permittivity of the void, of the empty space, which has a value, but also, for example, metal has a different value, plastic has a different value, and so on. And when a electromagnetic wave interacts with a material, the kind of interaction, or the amount of interaction, better, that happens, is governed by these two coefficients, which are, as I said, characteristic of the material. So the way the electromagnetic waves propagates and travels and interacts with stuff depends on the characteristics of the stuff itself, okay? You also find often Z, which is the impedance of the medium that we are considering. Z0 is Z with 0 is the intrinsic impedance of the free space, but okay, that's detail, which is basically the same thing, and it is a combination of these two coefficients. Is the same saying that the permeability, permittivity change is the same saying that the impedance is the intrinsic impedance of material is actually changing. This is extremely important because it is at the root of pretty much every situation and every piece of technology that we use from stealth. So keep this in mind, keep this in the back of your mind, put it away, and let's move on. The other type of interaction is reflection and refraction. Let's leave aside refraction, which is not very important for our lesson now, and don't care about what a magnetic resonant absorber is. What we're showing here is actually, what's important to see here is the reflection. And as you can see, the reflection is a pretty simple concept to understand. You have an inbound wave that is actually reflected. in another direction, and the angles of the impinging wave and the reflective wave are the same. This is the concept, this is the base concept of reflection. But what's important to understand is that you have a reflection because those two constants, this or the specific impedance, actually change, and you have the reflection exactly at the interface where those two numbers actually change. Okay, so that's the reason why they are important. Because every time there is a discontinuity of material, something happens. And that something is generally going to send electromagnetic energy all around, and this will become, and this will create a radar return or anything like that. So that's the reason why I was telling you it is so important. Let's move on with another point. Radar. On again, this is one of the graphics that I got from Aircraft 101, for example. What's the concept of detection of the radar? Well, you have something that actually emits some electromagnetic energy. The electromagnetic energy bounces off the potential target, and then it is received by an antenna usually often collocated with the emitter, but not necessarily. And from the reflection, you can actually identify an object. But here on the left, we have a very important concept in the sense that you have, in every electronic system, you have noise. At least you have thermal noise. That is, any electric circuit that is above absolute zero produces noise. Tends not to happen anymore with modern electronics. But when you use the old let's say older audio amplifiers in your old stereo systems. Now, when you turn them on, you started hearing a whoosh, something like that. That was noise, and a large part of that is thermal noise. Then there are other sources of noise that are interference, electromagnetic interference, or also mechanical vibration can generate noise, and this kind of things. So the signal that you are returning, that is coming back, needs to be well above the noise level, well above a threshold to be actually detected. But this is not simple, because it's not that simple as it seems, because you have situations like the false alarm on the left here, that is shown here, where you are pretty much at the threshold, and you can't really be confident if it is a real signal or it is not. So false alarms doesn't mean that something is actually badly designed. They are an unavoidable fact of any kind of detection system. You will have false positives. And with the recent facts of the unnamed virus that happened in the last 2 years, you will probably all became familiar with the concept of false positive. So you make a test, it turns out positive, even though you are not positive. Yes, that, mathematically speaking, is part of the noise that is associated. It's not exactly it is that. Then there is another concept. I have a strong signal, I make a detection, but how confident I am that is not a false alarm, that is not something else that's created a false alarm. So every time that you talk about detection of anything, you have always these two levels. The first one is the detection of the signal, and the second one is how confident the detection is right. These are this is another concept that is at the basis of every detection system, of every detection technology, of the target recognition technology, of anything like that. That is important to keep in the background, okay? Because you may have you will see later that may become important, and this is going and it is something that I would like you to keep in the back of your mind. Finally, radar cross-section. Finally, well, we have quite a lot to go through. I hope I don't fall out. I hope I don't fall unconscious during the during the lesson, but anyway. So, sigma, radar cross-section. So, in practice, radar cross-section is how well a body actually refracts radar radiation. Okay, as you can see, the rigorous, the actual definition is a limit, which is a mathematical operation. You don't have to worry about that. The key point is that you see here there is the ratio between two energies, the incident field strength at the target, which is, say, the energy of the impinging radiation radar beam, and the scatter field strength at the radar, which is the level of return of energy returned to the radar. Now, this definition is telling more than there's more than meets the eye in this definition. What I mean, so the radar cross section is rather intuitive. No, you see how big an object appears on radar, how much radar radiation is the measure of how much radiation the object is actually reflecting, and obviously depends by the object itself, by the shape of the objects and the material that is made. Yet it is defined as the ratio between two energies. Every time in engineering, if there is someone studying engineering or is going to study engineering, will be useful to have, will be useful to remember this. Every time you see an engineering quantity defined in this way by the effect, not by the cause, it means that we don't have the flipping idea on how to calculate that. Because the energies, this ratio of the energies is the effect of the radar cross-section. It's not the cause of the radar cross-section. As I was saying before, the cause of the radar cross-section is the shape of the aircraft. The fact that we define the radar cross-section in this way means that we have no analytical way of calculating the radar cross-section of an aircraft. This doesn't mean that we can't. We can use numerical methods. We can use approximate methods. We can use numerical methodologies. We can use approximate methodologies. I'm sure there are several ways of doing this, very clever ways. But if you give to a person the exact shape of an aircraft, you won't be able on a piece of paper to write some equation and calculate the radar cross-section. This was the reason why STALT didn't really progress till when it was possible to have very accurate simulations of the radar reflections on the aircraft. Until you didn't have proper equations that could tell you exactly what was going on. This was the work of Piotr Umfitsev. So it was a Russian physician that actually got the basis of this, that in Russia was pretty much ignored, but in the United States was considered very important and was actually used as the basis for the first stealth aircraft, for the calculations of the first stealth aircraft. So the takeaway is the radar cross-section is something difficult to calculate. But as I said before, the radar cross-section, even intuitively, depends on the shape of the aircraft. So the radar cross-section cannot be just one number, because the radar cross-section depends on the attitude of the aircraft. Here you have the radar cross-section of the Harrier just on the horizontal plane. If you go around the aircraft on the horizontal plane, and as you can see, it varies quite a lot, and there are directions where the radar cross-section is much higher than the rest of the aircraft, and it changes just to vary a bit. Those guys who you mumbled, could you please include them in the description if possible? You mean Ufimtsev, Piotr Ufimtsev? Yes, I can give you a pointer. Okay, well, I mean that work is really tough, huh? To read the theory and the basis of that work is really, really tough. Anyway, so the radar cross-section actually is depends from the attitude. So you have one number for every attitude from around the aircraft, above, below the aircraft, on the side, and so on. So when you see people who produce stuff like this, you legitimately have the possibility to, you are sort of authorized to doubt that they really understand what radar cross-section is. I gave some numbers for reference because it's always, you want to always know you want to know exactly what they are. But this is the sort of numbers, and the proportion between these numbers gives you a good idea of the differences between the aircraft. Notice, for example, that an average fighter aircraft has let's say has a surface of a few meters or some tenth, few meters or a couple of dozen meters, the largest one, while the F-35 or the F-22 have a very, very small radar cross-section, and that's probably from the best direction. So I believe that probably even the F-22, if you are illuminating it from right above, is going to reflect much more than that. It will still be low observable, but it's going to reflect much more than that. An interesting one is the one on the right, the corner reflector. So basically, these are these are items, are devices that are used often in maritime environment for the civilian ships to stand out on radars, which are basically objects that have two metal planes at an angle, for example, generally 90-degree angles, and you can have, and every radiation that comes on this side is reflected very strongly, and so you can have here he's saying that a corner reflector is 1.5 meter in size, can have 20,000 square meters of radar cross section, and this is one of the reasons why you don't see acute angles or 90-degree angles on stealth aircraft. This is interesting because this is one of the few cases where it's actually possible to calculate analytically the radar cross section. That is when we have a sphere. That's a typical case that. And the interesting thing is that is the comparison between the wavelength and the size of the sphere. So we see on the right, if the size of if the wavelength is much smaller than the radius of the sphere, then it is reflected pretty much optically. There's a normal reflection. If the two sizes are comparable, there is a region where something strange happens, which is called the resonance region. And if the wavelength is much larger than the size of the sphere, you have a region, you go into the scatter, you start having scatter. It's called Rayleigh region. The Rayleigh scatter is type of scattering, and so you see the rate. But what's important, the radar cross section goes down quite a lot. To the more to those of you who are more familiar with these kind of problems, this should tell you something about low frequency radars to identify stealth. It's basically telling you that, let's see if someone gets to the point. Can you tell me where is the problem here in using a long waves, low frequency radar to identify stealth? If you look at this chart, is anyone capable? Yes, please. Don't have this kind of fast. Yes, please chill, okay? There's no point, no winning. We are here to discuss. We are here to learn. We are here to have also some fun. Otis would kick you out probably if you found you sort of bickering like this, because he wouldn't understand why humans are actually having this kind of discussions. Fortunately, tonight Otis went out with the microwave oven, and I don't know where they have been, where they went. So, too low frequency and the scatter. T-GOT 5. Yes, my friend, you are perfectly right. You're perfectly right. So you can use low frequency radars, long wavelength radar, but not too low and not too long. So that's the point. That's the point. So there is an intrinsic limitation to the frequency that you can use. There's an intrinsic lower limitation, which is dependent on the size of the targets that you want to identify. Mind, an aircraft, eventually a bomber, for example, is definitely 10 times, so one order of magnitude, bigger than a missile, okay? Oh God, we are 55 minutes into the live stream and we are just getting out of the introduction. Okay, maybe try to be a bit quicker. Anyway. Okay, this is another key point that I would like you to reflect about, because it is again a foundational point to understand stealth technology and some stealth choices. No, Otis is not with us. He's definitely offline. He's not going to appear in the. He's not going to appear in the chat suddenly. Anyway, so the radar equation. The radar we said before we need energy traveling between the radar, the target, and back. Often you can for the radar, no, for the calculation regarding the radar, you express this in terms of power, which is energy in the energy actually developed, non the instantaneous energy, is the amount of energy that actually goes in time, developed in time, and that's secondary. The point is the intuitive concept of power is perfectly fine. What is important is that R4. R is the distance between the emitter and the target. And as you can see, the power is inversely proportional to the power received. The electromagnetic power received is inversely proportional to the distance between the emitter and the receiver to the fourth power. To the distance elevated to the fourth power. So R times R times R times R. Okay, 4 times. This is what does it mean? That the power that the radar receives from the target diminishes very, very quickly. It doesn't go down like a line. Some of you will be familiar with the inverse square law that is found pretty much everywhere in physics. It's even faster than that. It's twice as much as the inverse square law. And it is actually 2 inverse square laws. You may wonder, why 2? Yeah, no, it's actually obvious because while the power propagates from the emitter to the target, the energy and the power density diminishes with the inverse square law, like everything that propagates in space. And then the reflection from the target to the emitter then diminishes again with the inverse square law. So you have to multiply the two together. This means that the power that the radar receives diminishes quite a lot. And it is incredible the amount of power that is actually emitted and the incredibly tiny, minuscule amount of power that is actually received back, and what the amplifier and all the circuitry that is connected with the radar can do with just that tiny amount of power that is received. But there is something more interesting here. Look at the picture on the right. You have an inverse square curve and a fourth power curve. Then you have distance and power received. Distance on the x-axis, power received on the y-axis. Do you notice how the fourth power curve is actually more squashed toward the origin of the axis? It is much more this sort of hockey stick that you have there. It's not an hockey stick actually, but just to be clear, that sort of hockey stick that you have there is much more violent, it's much more abrupt than the inverse square law. So what does it mean? Since the ability to detect is sort of driven by the power received, you will have a long distance far away where you receive nothing, and all of a sudden, almost suddenly, the power that you receive jumps up. That's the reason why. That's the reason why targets tend to appear suddenly on the radars. No, so it's almost an L. Okay, you're in a situation in which either you don't see the target at all, and then target gets marginally closer, and then suddenly you have a much stronger return, and you can detect it. So, and it is sort of it behaves like sort of an L. It's sort of either you don't detect or you detect. No? So this has two consequences. The first is that, or better, it's just in two sense. So this is the point: is if you want to be stealth at a relatively long distance, it is relatively easy. But if you want to be stealth in the vertical side of the curve, then you have to reduce the radar cross section an awful lot. Look at the radar equation. Sigma, which is the radar cross section, is here at the top and has no power. So the power that the radar receives is directly proportional to the radar cross section. So to compensate a fourth power curve with a just linear curve, you have to reduce sigma a lot for many order of magnitudes. That's the reason why the difference between a normal aircraft or an aircraft or a low observable aircraft and a properly stealth aircraft seems, in terms of radar cross-section, even in those indicative values that we have, seems so high that is 1 and 0.5 compared to 0.0001. No, it seems an enormous difference. So you say, it's 4 order of magnitudes less, so it's probably invisible. No, it's not much more. Well, it is less visible, obviously, but I mean the difference is way lower than you may think because of this mechanism of the fourth power. I don't know if I've been clear. Okay, was this understandable? Please tell me if it was understandable. Is it? Sorry, I drink something because. Okay, in the meanwhile, talking about Ukraine, well, that's fine. Yes and yes. Sort of, yes, sort of. Okay. Yes, clear. Lambda square means you have a good reason to reduce frequency. Yes, sort of. It's slightly different. It's relative to the effective aperture and so on. So, now think. The Su-57, oh no, it's not that stealth. Or the J-20, oh no, it's not that stealth. Against the F-22, which is very stealth. B-2 is very stealth. The F-35 is very stealth. No, these are two philosophical choices. Since you have to put an enormous effort for a small gain, because you need to reduce the radar cross-section a lot, China and Russia have simply decided to accept to have to be a little less stealthy, but they will still be stealthy. They will be have a significant advantage of the on the completely non-low observable systems with a reasonable reduction, with a reasonable effort. So they decided that they will take full advantage of pretty much the horizontal or nearly horizontal part of the curve, but they're not doing any effort to go on the vertical part. The Americans took a different approach and they said, no, that's despite the fact that it's very difficult, we want to reduce the radar cross section because we want to be as stealth as humanly possible, because we believe is an enormous advantage. So these are two philosophical choices. In fact, I don't buy the fact. I don't think that it's probably Su-57 and the J-20 are probably less stealthy, but not that much less stealthy than the other aircraft. In practice, the distance at which they will be identified is not going to be much longer as the radar cross-section would lead you to think, okay? And considering that a stealth aircraft you can identify at 10, 20 miles, sometimes 30, depending on the situation, then you will have a Su-57 or J-20 that can be identifiable at 40, 50 miles, while a Su-35, for example, will be, or a MiG-31 will be identifiable at 200 miles, okay, because he is not particularly stealthy. So this is a pretty important idea that you want to, pretty important idea to thing to understand, the nature of the power, the fourth power, the inverse fourth power of the distance in the radar equation actually dictates the tactical choices that you're doing. Okay, this was probably the most difficult concept. Everything else is actually simpler, and we still have quite a lot to go. It is possible that I will probably completely worn off, but I keep soldiering on. So maybe we can't cover infrared, where we'll cover a different thing, but let's keep going and see where we get. This is okay. After that, something simple. This is just for information. These are the names that are generally used when we speak about radar bands. In the sense, we classify the frequency and the wavelengths normally with a name. There's no actual discontinuity between the bands. It's just a way of speaking of a range of frequencies in a friendly manner. This is not the only classification. There are various classifications, and what is confusing is that they have pretty much the same names. So, but they have different bands. So, what you're seeing here is probably the one that is mostly used in the publications and so on. So, just to be clear, the X band is the one used mostly for aeronautics detection. It's the band where almost every radar or every fighter radar is actually working on. As you can see, we are talking centimeters. Is also the band that is used in for active seekers in missiles. Even though in that case, sometimes you also use the Q band, which is very, very, very precise. Patriot, I think, uses the Q band, for example. C band is a sort of a hybrid. Normally, OWACS and the ground surveillance radar use the S band and the L band, and sometimes the L band. The Russians tend to make a lot to use the L band quite a lot, because yeah, it helps in because the radar cross section depends from the wave. The radar cross section actually depends also from the wavelength, and sort of better. We'll see later. It's better suited for the stealth, and UHF, VHF are bands that are normally used for communications, for radio communication, but can be used, but today can be used as radars. Please don't fight about Ukraine and Russia. Please don't fight about Ukraine and Russia. But anyway, so this is just a naming thing. I'm sort of giving for granted that someone knows this in the future. It would be useful to actually memorize this so you can read when you read actually document a paper or anything, you know pretty much what they're talking about. Okay, now let's talk about radar propagation. The propagation, what is the flip, don't tell me. Okay, as you can see, the propagation of electromagnetic, really I hate PowerPoint on the Mac. It doesn't caches the videos, so here's the result. You have still images basically. So since the planet is not flat. Okay, the Earth is not flat. The Earth is not flat, despite the fact that some people think it is. And one of the way of actually proving them wrong is the fact that the propagation of the radar radiation tend to become sort of parallel to the ground, considering the geometry of the situation. So when the radiation gets to the aircraft, it generally has a very small angle with the horizontal direction, which means that the most important direction where you want to be low observable is from the horizontal. 360 degree eventually, but from the horizontal, because you will hardly have any radar just below you or any radar just above you. There will be a bit above you, a bit below you, but just for the geometry, they won't be exactly above you or below you. So the kind of stealth you want to have is from the side. But this means that the aircraft is flying flat, because in this case, every time you maneuver, if you manage to obtain low observability from the side, and you become inclined like this, your low observability is pretty much gone. There is an interesting witnessing, declaration interview to one of the pilots that have been of the F-117 that were flying over Serbia. And they said that their instinct, if they were warned by a missile launch, was actually to try evading, but they were trained to keep flying flat, just not to increase their radar cross-section and to show the radar areas that were not low observable, because the missile that was launched was, you would only, in that case, you would only have simplified the life of the missile guidance, because you will become much more observable if you evade. So that's one of the things. So so stealth is important from the side. This means and so, and what you have on the side is actually reflections. The main contribution that you have from the side is actually the reflection. Now, it is quite interesting to learn that while the reflection always happens, the reflected beam is not necessarily as precise as the impinging beam, because the electromagnetic radiation is coming just from one direction, but when it is reflected, depending on the wavelength, it can be reflected actually in a cone rather than on a single direction. So at low frequencies, the reflection is much larger. This is one of the reasons why low frequencies are better against stealth, because at higher frequencies, if the aircraft manages to reflect away in a different direction the electromagnetic energy, you are done. But at lower frequencies, since the reflection is not just in one direction, but is sort of scattered around, it is still possible that some of the energy reaches the target. So, as we've seen before, the radiation, the direction is almost horizontal. So what do you want to do basically? When a horizontal beam arrives, you want to reflect it away, either above or below you. And this means that you have vertical surfaces, that you don't want to have vertical surfaces on your side. You don't want to have 90 degrees angles. You also want your winged surfaces and edges are in direction that deflects the energy away. And also curved surfaces in a specific way can be useful to limit the reflection that you have. Now, this kind of radar reflection, the geometric specular reflection, is by far the main contributor to the radar signature of the aircraft, or say the main contributor to the radar cross-section, total radar cross-section of the aircraft. Do it right on the specular refraction, you are halfway there, okay? How about using bistatic radar to detect stealth planes? That's exactly the point. If, like sorry, but that's a fact. Like the Russians do, if you have an integrated air defense where the emissions from one radar can be received by another radar and they can be actually compared, so the emitter and the receiver are not co-located, is one of the ways where you can have more probabilities to detect stealth. Still complicated, but yes, it's one of the countermeasures. The fact that the oh, thank you, Carl, much appreciated. Yes, I will probably need a 4-pack of beer tomorrow. Anyway, what time is it? Now, yes, definitely I will crash and burn before infrared, but I want to finish radar. So this is a picture that I actually nicked from the Discord server. Apologies, I don't remember who actually posted it, but it's very interesting. These are the acquisition boxes of two Soviet radars that work at low frequencies, that work in also that work at very low frequencies in VHF frequency, and this is the case where actually the reflection is not in a specific direction but is all around. The final result is that you have these acquisition boxes that are very large, and you have a relative large incertitude in the measure. So you see that at 50 nautical mile, while the distance, the position is relatively easy to, the distance is relatively easy to measure because based on the time the reflection that the signal takes to go from the emitter to the target and coming back, and we can measure times relatively easily and with great precision. In the other two directions, in the x and the other two directions, you have a large incertitude, and at 50 nautical miles is about 1 kilometer. At 100 nautical, at 200 nautical, at 100 nautical miles is about 2 kilometers. So there is quite a large incertitude. There are some, and this is not just systems like Michael A. Mayo says, geez, that's kind of precise. With another radar, you can get it. Yes, that's right. That's the key point. That's the key point. If you have more than one radar and you intersect the two boxes, you can pinpoint quite precisely. Yeah, but don't spoil the the videos and the lessons about the ways of countering stealth. Anyway, so what I want to show you is that the radar, while with an X band, for example, you can have precision that are the orders of few meters. In this case, you have hundreds of meters, a couple of kilometers. I happen to hear pilots saying that when they get the distances from the OWACS, from the OWACS, when they have the direction and the of a target, the data of a target from the OWACS, they have incertitudes that are particularly in height, particularly in altitude, that are measured literally in thousands of meters. So they don't know exactly, until they don't see it on their radar, they don't know exactly where it is. So, okay, please stop. I'm not approving any of these messages. Please stop bickering, okay? Okay, so otherwise I ban everyone and that's it, okay? I don't want to do that. I hate doing that. But please stop bickering, okay? There's other people who are actually interested in the... At JADU 79, do airplanes not have the opportunity to be warned if they're hit by a radar long before the radar can see it, so they can avoid them? Well, yes, but what is he trying to plug the toaster? I have a George Foreman's toaster, so yeah. That'll make me think. Yes, but you need to be in a tactical situation that let you actually avoid the radar. Okay, this is not guaranteed. Okay, moving on. Okay, this one. Okay, here we have an F-15, which is an aircraft that doesn't particularly have any stealth properties. And as you can see, the tail and the side of the aircraft is vertical, which is the worst thing for the radar reflection. Okay. The other problem that you have is is often on the air intakes, because the air intakes are actually, in many aircraft like the F-14 or the Tornado, are actually square in section. So you have a 90 degrees, or a number more than one 90 degrees angles. And before we mentioned the radar, the angular reflector, that is one of pretty much the best reflectors that you can have. And in aircraft like this, like Tornado, um, those air intakes are pretty much one of the best reflectors that you can have. You probably need, particularly if the aircraft is maneuvering, they become immediately a very bright, very bright, very bright flash. Also mind that 90 degrees angles have the property of always reflecting the radiation directly toward the direction where it came. So there's no way of making a 90-degree angle stealth. And also, as you can see, you have a 90-degree angle at the intersection of the wing and the fuselage, the intersection of the pylon and the wing, and in plenty of other places. All that thing is a no-go. If you have seen the video about the J20, I said, yes, the canards are a problem in terms of stealth because they reflect energy, but the angle between the canards and the fuselage is not 90 degrees as it nor it is, or near 90 degrees as it normally is, and this means that they probably try to mitigate this effect. How effective it is, we don't know, but that is one of the things. Let's move on. Another important element is the so-called planform alignment. Okay, here we see the YF-23, where this is absolutely obvious. You have all the edges of the surfaces and many other edges on the aircraft that are all aligned in the same direction. Why? Well, here we don't have just reflection, we have diffraction, we will see in a minute, but also these edges actually do produce a reflection. If you keep these edges all aligned, even all the reflections will be aligned. So you will have one direction that will depend on the emitter, on the position of the emitter, where the aircraft won't be stealth because all the reflections will go in that directions. But in the rest of the 360 degrees around, you won't have any reflection. So you will be low observable everything else from every other direction. Okay, so the idea here is where you can't, while normally you want to, well, so far we have seen situation in which we want to avoid horizontal reflections in this plane. In this case, we are looking from above and we want to avoid horizontal reflection directly toward the emitter, but we want to deviate them somewhere else. And yes, if you have a receiver in that direction that is lucky, the aircraft can be picked up and won't be stealth in that direction. Jesus, takes, what time is it? I've been talking for 1 hour and a half. Okay. So let's, guys, definitely we won't be finish everything. Let's try to, I soldier on. but I don't want also to actually use too much of your attention because okay, when we hit 2 hours we stop and we will have something else and we will keep going. Now, this is interesting. Curved surfaces. Now, if you have a curved surfaces a circular section, and you have some incident radiation, you are pretty much guaranteed that there is a point where the reflection will go directly toward you. And this is the case in here. As you can see, this is the electromagnetic radiation going in, and since it goes exactly here at the center where it's pretty much 90 degrees with the radiation, it reflects right back. However, is enough to move a little bit, and the tangent won't be 90 degrees with the radiation, so you will have a reflection and it will go somewhere else. So this is the reason why you can see stealth designs that are a mix of very jagged, very edges, very flat and irregular flat shapes, and then rounded shapes. The F-35 is full of stuff like that. Yes, because with a curved surface, at the cost of a minimal reflection toward the guaranteed minimal reflection toward the emitter, everything else will be scattered around. So it's not that bad. Let's say sort of mitigates the radar reflection. And now you will tell me, yes, but this is what happened. But most aircraft have a sort of a circular section of the fuselage. So are they stealth? Well, it's the circular section of the fuselage in itself is not terrible, but you will also have a lot of, for example, 90-degree angles. You will also have the stores, the external stores. You will have the wings, you will have the tail, and all these kind of things. So yes, a circular fuselage is not that bad. It's not really stealth, but it's not that bad, even though you see less and less of those. But I mean, as a secondary way of actually scattering around the radar radiation, the radar waves, yes, it may work. One interesting summary of all these technologies is the new Korean aircraft. The F-21 Boramae, I suppose that's the pronunciation, I'm sorry. So these are the typical traits of a stealth aircraft. So you have this edge on the fuselage, and you can see the radiation coming horizontal will be either reflected upward or downward, and the same you see on the side of the aircraft. It is flat, but it was also inclined, and so the radiation will be reflected downward. And crucially, the angle with the wings is not 90 degrees, so it's not a terrible, is a relatively flat angle, so it's a less effective reflector when the aircraft is maneuvering and receives some illumination. Again, the tail is canted outwards, and that's a typical case. I don't think you will ever see a stealth aircraft with vertical tails because they are very strong reflectors, and also the air intakes are not rectangular in shape, are sort of a lozenge, again to reduce the 90 degrees angles and simplify the say reduce the kind of reflection you can have inside. Then the air intakes is one of the most misunderstood subject in stealth, in say in the educational, in the press, is one of the most misunderstood subjects. But anyway, also it's quite interesting here where you see I actually see the cannon housing, the housing of the cannon. No, that is this one doesn't have any flat surface to do the reduction, but they have probably the engineers have made an assessment, and they thought that say a curved, a rounded cover was good enough in terms of stealth, and it wasn't compromising too much the aerodynamics. I quite like this aircraft because there's all the typical signs of a stealth aircraft, yet the Koreans say that it's not a stealth aircraft because it doesn't have rather absorbent materials and some other measures. Well, once you have done this, once you have addressed the specular reflection, you are pretty much halfway through. Let's say you have already used the horizontal part of the hockey stick, or most of the horizontal part of the hockey stick. So this is something that is definitely worth doing, even though you don't have any other rather cross-section reduction measure in place, because this itself is going to be relatively effective. Okay, so far specular reflection easy to understand, but it's not everything. There's another quite important source of reflection that is addressed on many stall design, which is the one caused by scatter and diffraction. But before discussing scatter and diffraction, is also important to understand another concept. When electromagnetic radiation is impinging onto a metal surface, it actually creates into the metal a traveling wave. So there is an electromagnetic wave that is actually traveling inside the metal, typically horizontally, and parallel to the surface of the metal, in the sense that, okay, typically we are talking about the cladding of the aircraft, now the plates that cover the aircraft, which are sort of flat, so they travel horizontally. And okay, this message can go. And this is something that has quite a lot of effect. In fact, when we have, we tend to have scatter around the edges, which is, as you can see, for example, at the tip of the radome, at the tip of the tail, and so on. But also we have a particular type of scattering, which is particularly nasty, and so it says it is not negligible in terms of return, which is the scattering from a sharp edge that you see there, where you have an incoming radiation that comes into an angle, and then it is scattered around in what is called the Keller cone. And since even though the frequency is very low and the reflection would be normally specular, because of the because of this mechanism, it's actually reflected in this sort of a cone, and it's good to minimize it. And the effect is also compounded by the fact that on the tip of the wing, if there are no mitigation measures in place, there is a traveling wave excited by the electromagnetic radiation that actually contributes to strengthen the return. So this is particularly nasty situation. Okay, this is actually the way the Keller cone is actually working. The angles are pretty much the same and so on, okay? So where do you have this kind of scatter and diffraction? You have the sharp edges, but you have them at sharp edges because you have very strong discontinuities. Do you remember at the beginning we said pretty much everything that happens is because the intrinsic impedance is actually varies abruptly, and so something happens. Yeah, that's the case when you have an edge. And mind the size of these edges are sort of the same size of the wavelengths that are actually involved, so they actually interact pretty much strongly. Every time you have a discontinuity, you have some scatter. This picture, again, that I nicked from Aircraft 101 is extremely clear and extremely important because every time you have a surface discontinuity, every time you have a change in material, or at the edge of the body, every time you have a gap, and so on, then you have some form of emission. When they say that the rivets of the aircraft or the joints on the aircraft create a radar return, yes, they create a radar return, but they don't reflect, they scatter or diffract. The radar return is not a reflection, it is this effect. And you want to avoid it. So you want to have materials that are either very homogeneous, so the impedance doesn't change much, or, extremely important for radar absorbing material later, doesn't change abruptly. It changes gradually. In that case, yeah, you may have an absorption, for example, rather than a reflection, and absorption is something that you want. So you always have people saying, but Sukhoi 57 is not stealth because there are all those rivets that are actually exposed. Yes, it's true, and the reason is this: a rivet is a discontinuity. On the American aircraft, you tend to see them covered. There are not that many that are actually visible outside. There's just a few. In fact, in the production aircraft, there are way fewer rivets actually exposed. They are all covered, and this is one of the reasons. How well does rust like on F-35C affect returns? Well, rust is a change, is a different material, is no longer metal, is an oxide. So the intrinsic impedance has changed, and so yes, they potentially cause a return. Where does the magnetic energy goes, Alberto Tarantino, where does the magnetic energy goes in case of absorption? Heat. It warms up a little bit. Yes, graph 55, the Su-57 have less exposures for the final models. Yes, that's true. There are way fewer gaps and panel gaps or rivets actually exposed in the Su-57. So the Su-57, this aspect of the stealth is taken care of in the Su-57, albeit if you if you watch the details, not as radically as the Americans do. Um, the fact the fact that you have a traveling wave that sometimes is called a creeping wave, but calling it a creeping wave seems creepy, so I prefer calling a traveling wave. So the fact that you have a traveling wave and discontinuities causes something that you see here, that you see depicted here. You have a traveling, in this case, for example, you have a traveling wave that goes around the fuselage, and every time it finds a discontinuity, there's the potential for a return. This is something that needs to be addressed if you want to be really low observable. And it is a non-negligible effect. It's something that is worth taking care of. You're still in the horizontal part of the curve. One case that should be probably enormous is this one. The Mirage 2000 famously has these ginormous uh, drop tanks. The return of those things that are actually made probably with with cylindrical elements. So the traveling wave can go in circle and go around. The return of this is probably very high. Another source of the scatter and diffraction is the junction of the mobile surfaces with the rest of the aircraft. There you must have a gap because otherwise the surface wouldn't move, and that is a source of that is a source of diffraction. In in fact, in stealth aircraft, there's normally a flexible band of a conducive material that is placed there to reduce this effect. Doop, doop. Another way is having serrated surfaces. This in I don't know exactly what we are seeing here because it seems a strange uh, episode of worship. So they are actually worshipping some elements of the aircraft, but the here you can see in several places on the F-35 the serrations on the panels. It is that jagged border where the panel edge changes direction very often. Why this is useful? For two reasons. First, because normally serration is aligned with the planform, so the direct reflection that you may have from a panel is also aligned with the reflection that you have elsewhere. But also in this case, the traveling wave that generates the Keller cone on the edge of the panel has a much shorter run before there's much shorter space to run before encountering a discontinuity and being diffracted around. So the jagged panel contributes either by reflection or by diffraction to pretty much scattering around the energy that is actually received. That is another typical trait of stealth aircraft that you see pretty much everywhere. If they're worshipping the landing gear, is that technically a foot fetish thing? Please don't. I don't want to be demonetized. Don't let me reply to that. Long live the landing gear. If it is not prayed to, it will break on you. Okay. At least cylindrical drop tanks can be dropped and thus possibly act as the cause. Interesting point. I never thought about that. They're pretty much to tell apart, probably, and they're very short-lived. But I don't know. Maybe they could be useful in some situations. I don't know. Anyway, Here is another element of serration. So you see other panels on the surface of the aircraft that show this kind of serration. And in this case, on the top of the F-35, you can see that probably these are the areas of the aircraft that can be removed for maintenance, for accessing some internal parts. And they are actually covered with this band that is probably a conducive, um, sort of conducive surface that guarantees the electrical continuity between the panels, but it's probably also a rather absorbing material of some sort on top of it, so it should be probably something strange, but it's clear that here there is an effort to reduce these kind of discontinuities that create all these kind of things. Then there are some discontinuities that you can do without. For example, this white thing is is the data link antenna, and there is no way you need an electromagnetically transparent slot for the antenna, and there's nothing to do with that. Anyway, also here, this is also interesting. You see this device here, this small thing here. This is a radar reflector, so probably contains a lot of elements, 90-degree elements in there that actually is mounted on the aircraft to increase its radar cross-section when you don't want to give away the real radar signature of the aircraft. When they're flying during transfers or in a civilian environment, they use it. At the wingtip, yes, we get it. What's happening on the wingtip is you get in a minute. You see that these kind of gray things on the F-35s also happen on many other edges, and it happened on the F-22 as well. You can see them on the J-20, you can see them on the B-2, and so on. These are another mitigation measure of the diffraction that happens at the surfaces. In fact, see, you have the Keller cone, and one way to reduce the edge current that is actually contributing heavily to the generation of the Keller cone is actually attaching a band, which is actually part that progressively becomes from very conducive, like metal, to non-conducive at all. That is, the current at the tip of the cone in here is pretty much non-existent, and it is progressively changing. But since the electrical resistance, the electrical impedance of this band, of this covering, varies smoothly from being completely conducive to being not conducive, you don't have much of a reflection in this case. You have since the transition is quite smooth, you are actually minimizing the reflection. It is working 100% as usual, no, because there are always imperfection, discontinuity stuff that you don't account, but it is the reason why you often see these bands on the stealth aircraft along the edges. What are your views on the mirror coatings? They're probably related to infrared. That the serious analysts that I've seen around, they believe it is actually related to the infrared. It's a new type of infrared suppression materials. It's almost 2 hours. Okay, I keep going. Okay, let's do the intakes, and then, guys, I'm sorry we stop. We will do something, yeah, probably this week to keep going, where we will probably be another 2 hours, in which in the first half an hour we'll very quickly go through what we've seen tonight, and then we'll go with the rest. But now we cover the air intakes, because this is one of the areas where there is pretty much the most is the most misunderstanding how the problem is. So the effect the effect of the air intakes changes with the frequency and the wavelength that we are considering. At long waves, pretty much with the long the conduit of the air intake is not large enough to let the radiation in. If the wavelength of the radiation is near or larger than the characteristics measures of the air intake, it won't get in. So it will be basically, as you can see in this beautiful animation that I did, it is pretty much reflected by the mouth of the intake, and the only kind of measure that you want to reduce, that you want to have, is actually adding some rather absorbing material at the intake to reduce this kind of reflection. However, the situation changes, and quite a lot, when the frequency of the radar is pretty much similar to the size of the air intakes. No, sorry, these are still the long waves, start being. So medium waves. So in this case, the duct behaves as a waveguide. A waveguide is something that you see in radar typically, that actually brings is used to bring electromagnetic radiation to sensors and so on. Is way used in radar, and it's a normal concept. But I mean, the air intake duct behaves as a waveguide. In this situation, the energy pretty much is transmitted through the conduit into the conduit with pretty much minimal energy loss, gets to the vanes that pretty much every aircraft has in front of the engine, and then gets reflected. And then it is reflected, and again with minimal loss of energy, gets out of the air intake, and it is a big, powerful flash that goes back to eventually goes back in the direction of the emitter. So every aircraft, depending on the size of and the shape of the air intakes, has a narrow band of frequencies where they are absolutely incredibly bright. Exactly because of this phenomenon, where it is actually behaving like a waveguide, where the duct is behaving like a waveguide. And the way to mitigate this is actually using tuned specific radar absorbing materials inside the duct, so that you try to absorb some energy. Also notice that in the two cases that we have seen now, the reflection happens either at the mouth of the intake or at the vanes before the engine compressor. So the engine compressor is not reflecting any wave, and is not the effect of the rotation of the compressor is not modulating the reflected energy. So the engine at long and medium waves is invisible is invisible to the radar, and also the modulation to the reflection that happens because of the rotation doesn't happen, and so is not invisible. And so this is a problem very important for automated target recognition that uses exactly this type of modulation of the signal to as one of the most important signatures of the characteristics of the aircraft. And so this is a, I mean, this means that you can do automatic target recognition with long waves, for example. You need to have shorter waves. But this is an entirely different can of worms. Then there is a third possibility in which the frequency is much smaller than the size of the intake. In this case, the waves, the electromagnetic waves, enter into the duct, bounce around into the duct, go through the vanes because the gaps between the vanes are probably small enough to let them go through. They're actually reflected by the compressor. In this case, the modulation of the reflection happens, and then they bounce back and get out of the and then they get out of the intake. The mitigation in this case actually lining again adding some other and different radar absorbing material in the conduit to absorb the specific frequencies that are most evident, most reflected the most in this situation. Now, this is what happens with the air intakes. At long waves, they're pretty much, they don't let anything in, so it's pretty much a reflection like another. There is a narrow band of frequencies that is actually pretty much the same as that is actually the resonant frequencies of the conduit. The conduit acts as a waveguide, and in that situation, they are a very brilliant reflector. Or at short waves, the energy enters the conduit, bounces around, and is reflected not by the vanes in this case, but by the engine compressor, and it comes out. So, in all of this, the S-duct, to shield or mask the compressor, what it has to do? Then, with this kind of situation, why stealth aircraft have an S-duct? Seems that it just depends on the frequency of the radar and the size of the duct. Doesn't change much. Everybody's telling you that the S-duct is there to mask the compressor. Is not true. Or better, yes, it sort of helps to minimize the potential direct reflection that at short waves you may have from the compressor, but you need to aim very well to have that kind of compression. Is just the two aircraft going head on. In that case, you may actually be in that situation. Now, the point is just to have a longer conduit, so the bouncing around happen, or the length that the radiation have to go through is a bit longer. So the radar absorbing material that you're putting inside have more time, more bounces, more reflections to be effective. It is definitely, in respect to geometrical masking of the engine, the importance of having the right radar absorbing material in the conduit is definitely higher than the effect of the geometrical masking. The only reason why the geometrical masking may be important is because in that case you have a very strong modulate, if you have the right frequency that gets directly into the compressor and bounces back, in that case you have a very strong modulation of the signal. And so if you do automatic target recognition from there, you can easily infer the type of the engine and then the aircraft model. But it is a particular situation that doesn't happen often, happens just in particular situation. In normal situation is way more important the absorption, the radar absorbing material within the conduit. Could you vary the diameter of the air intakes with depth to avoid the resonance? Yep, it's something that is done actually. They tend, I mean, the size of the conduit is normally the smaller compatible with the engine, and it is dictated by the necessity of feeding the engine. So you can't play a lot with that, but it is actually done. It is actually done. They again, the Rafale has the section of the section of the conduit of the Rafale. You can see that actually changes between. So that's one of the reasons. Guys, sorry, it's more than 2 hours. I am completely knackered. I need to stop. We are we are 65% into the presentation. Yeah, so how was it? Was it clear? Is there anything else you want to ask? Is there any question you would like to address? We can do 10 minutes of question, 15 minutes of question and answers, and then we will have another we will have another live stream to complete the thing. Thank you. Good job. Thank you for the lecture. Okay, good night. I see that after 2 hours, yeah, you are tired as well. Thank you, man. Is there any question? We can 5 or 10 minutes. We can have a round of questions. Can satellites be used as radars against stealth aircraft and missiles? Yes, you need to have a lot of satellites, though. Does S-duct masking possibly block infrared signals that could escape from the compressor or the near-infrared signals? It's not very hot. The compressor is hot, but is not terribly hot. Yes, the S-duct is also useful for that, but it's not a big contribution. So, all in all, it depends. Thanks for your work, was great. Yes, it always depends. In engineering, it always depends. Did you teach at university? No, never. No, never. Unfortunately, never had an academic career. I wasn't good enough. How much beer will you have tomorrow? But probably just one beer, to be honest. Much appreciated, Gus. I think most of it stuck. Very good presentation. Thank you very much. Very interesting. How much more effective are gallium arsenide radars against stealth, since it can detect smaller objects at long ranges? No, they are just more sensitive, so they just can process smaller signals. It's not specific for stealth. A ground, they are important because they're using as a radar, but in theory, and then they can fit in an aircraft, but in theory you could have a ground radar that has no size constraint that is as effective. Can further manage to pay attention despite being knocked down by COVID boosters shot side effects? Thank you very much for the effort. Can't wait for the second part. Can you please clarify the difference between RF energy and RF power? So a lot of people confused about that. So this is a general physical concept. The energy is the energy. The power is the energy time multiplied by time. So that's just a physical concept. Is not There's nothing deeper in that. Starlink lends itself to ER detection, I'd say. A constellation like Starlink can have military application, yes. S-duct is almost very necessary to mitigate opponent ATR and CTR system. Yes, that's the point. That's the most contribution is not to you are screening the compressor from X-band radars mostly because of the modulation that it creates, not because of the strength of the signal that it creates. Can you do an episode on electronic warfare generally? E18 Growler more specifically. I've been wanting to do that for a lot of time, but I don't think I know enough. But one day we will do that. Could you please clarify the difference between, okay, the same question. Please hit like. Yes, thank you guys. Please hit like. How will stealth be different in the sixth generation of fighters? Who knows? Who knows what they're going to come up with? Okay, guys. Any other question? Interesting or even just stupid, or questions have their own dignity depending. Anyone who's confused how the difference relates to this discussion, please hit me on the Discord. Yes, happy to. Can a radar receive and process a signal it didn't send? Yes, of course, there could be static radars. They are a very old concept. The first radars, the British radars that were used during the Battle of Britain, were be static radars, and it's often used, and it's probably one of the best bets to actually detect stealth. What have you studied? I studied aeronautical engineering at the Polytechnic of Milan, 5 years course when the 3+2 was not a thing. I'm old enough. Can one conclude the tactical use of a stealth plane by design, like Russians have very carefully designed leading edges and conventional engine nozzle, or is it a wage? Sorry, I don't understand the question. FL 300. Good night, good night. This is so illuminating. Thank you very much. Will F-35 reach 25K per flight hour? No flipping idea. It tends to be quite expensive, that guy, anyway. Could an air-to-air missile be stealth? I don't see why not, honestly. From above, stealth aircraft are less stealthy toward detection of radar. Absolutely, they're way less stealthy. Way less stealthy. Valerio, all the best. It's a tall proposition. It's a tall proposition, and Turin is a great school. Okay, we end here. I need to rest and probably hydrate myself again, and probably need to eat something else because it burns a lot of calories doing this kind of things. Anyway, thank you very much, guys. Thank you very much for being here. It's enormously appreciated, and have a good night.